Okay, let's dive into one of the most violent, most extreme, and frankly, most bizarre objects in the entire universe. We're talking about neutron stars. They are born from the absolutely spectacular death of something truly magnificent, a cosmic cataclysm that leaves behind an object that's almost too strange to believe.
So, what even is a neutron star? Well, at its heart, it's basically a single giant atomic nucleus that's the size of a city. I want you to try and picture this. You take something as massive as our sun, or even more massive, and you crush it. You squeeze it all the way down into a space that's only a few kilometers across. It's matter compressed to a level that just breaks your brain. And to really wrap our heads around that density, let's put a number to it. If you could somehow scoop up a single cubic centimeter of a neutron star, we're talking a tiny little speck, it would weigh 1 billion tons.
That's right, 1 billion tons of matter packed into something the size of a sugar cube. Another way to think about it is cramming all of Mount Everest into a single coffee cup. We're talking about a density so extreme it just completely shatters our everyday understanding of how things work. So you gotta ask, how in the universe does something like this even get made?
Well, it all starts deep inside a really, really big star. See, for most of its life, a star is locked in this epic battle. On one side, you've got gravity, just relentlessly trying to crush it inwards. And on the other, you have the furious energy from nuclear fusion in its core, pushing outwards. For billions of years, it's a perfect cosmic tug-of-war, and the star is stable. But that balance can't last forever.
And this is where things get wild. As the star gets older, it starts fusing heavier and heavier elements, and the whole process just accelerates like crazy. Look at this. Fusing carbon into neon, that takes centuries. Then just 1 year to fuse neon into oxygen. A few months for oxygen into silicon. And then, in its final, frantic day of life, it burns through all its silicon and creates iron.
And that right there, that's the point of no return. See, iron is basically nuclear ash. You can't get any energy out of fusing it. In fact, it consumes energy. So, just like that, the furnace at the heart of the star shuts off. The outward pressure just stops. And that cosmic tug-of-war, it's over.
With nothing pushing back anymore, there is absolutely nothing left to stop gravity. And what happens next is one of the most catastrophic and truly spectacular events in the entire cosmos. In less than a second, gravity wins. The core implodes on itself, crushing protons and electrons together, forging a brand new substance made almost entirely of neutrons. Meanwhile, the star's outer layers are now in a freefall, slamming into this new, impossibly hard core at a quarter of the speed of light. They don't just stop, they rebound in a titanic shockwave that rips the rest of the star to shreds in the universe's greatest fireworks display, a supernova. So, once all that dust and chaos from the explosion finally clears, the collapsed core is what's left behind. A brand new neutron star. And believe it or not, its properties are even more mind-bending than the explosion that created it.
I mean, we are talking about compression on a scale that is just, it's hard to even process. You've got the mass of about 1 million Earths, all squeezed into a ball so small it would barely cover a large city.
And it is so hot. Our sun's surface, which is already pretty blistering at 6,000 degrees Celsius, is nothing. A newborn neutron star starts out at 1 million degrees. It's a pure cosmic furnace. The only thing in the universe with stronger gravity than a neutron star is a black hole. It's so intense that it literally bends the path of light that's trying to escape it. This creates this really bizarre optical illusion where you can actually see the front of the star and parts of the back at the exact same time. But as crazy as the surface is, the real mystery is what's going on inside. Now, a neutron star has a structure that sounds familiar, a solid crust over a liquid core, kind of like a planet. But the stuff that crust and core are made of is unlike anything else in existence. So what is this material? I mean, what kind of matter can possibly exist when it's being crushed by that much pressure and density? Well, physicists have an amazing and wonderfully weird name for it. They call it nuclear pasta. Deep in the star's crust, the pressure gets so intense that individual atomic nuclei get squeezed together until they touch and merge, losing their normal round shape and forming these long, complex structures. And this stuff, it is calculated to be the strongest material in the universe. We're talking billions of times harder to break than steel.
And this just shows you how strange things can get. Depending on how deep you go, the nuclei arrange themselves into shapes that physicists literally describe as spaghetti, lasagna, and all sorts of other forms. And get this, lumps of this pasta can form mountains on the surface. Now, they'd only be a few centimeters high, but they would be as massive as the entire Himalayan mountain range. Just incredible.
So what about the very center, the core of the core? Well, the honest answer is we just don't know. The conditions there are so extreme that they're beyond our current understanding of physics. Some theories guess that the neutrons and protons themselves might dissolve into the sea of their basic building blocks, something called a quark-gluon plasma. Others imagine an even more exotic state of matter called strange matter. This is truly the frontier of science.
But these things don't just sit there. Oh no. They're born spinning like cosmic ballerinas, and they wield magnetic fields of unbelievable power. And sometimes, when they have a dance partner in a binary star system, their performance ends in the most violent way imaginable. Because they've collapsed from something so huge, they spin incredibly fast. Think of an ice skater pulling in her arms. Some of them become pulsars, spinning hundreds of times every second, sweeping beams of energy across space like a cosmic lighthouse. Others become magnetars, and these things have magnetic fields a quadrillion times stronger than Earth's, so strong they could wipe your credit card from halfway to the moon. But the most spectacular fate of all is for a pair of neutron stars that are locked in orbit around each other. Over millions of years, they radiate away energy as gravitational waves, those ripples in space-time itself, and their orbits get tighter and tighter. They spiral closer and closer until they smash into each other in a cataclysmic explosion we call a kilonova. So why is this so important? Why does this epic collision matter to us? Because it's in the final, fleeting moments of that ultra-hot, ultra-dense collision that the universe forges most of its heaviest elements. The gold in your jewelry, the platinum in your phone, the uranium that powers our reactors. Almost all of it was made in the death spiral of two neutron stars. I mean, just stop and think about that for a second. To create the gold in your ring, a massive star had to die once to become a neutron star. And then, that incredibly dense remnant had to die again in a collision with another one. The very atoms that make up our world, our technology, were forged in that double death and then flung across the cosmos on a 13 billion-year journey to eventually get here. We are, in a very, very real sense, made from the ashes of these impossible objects, and that is just a truly incredible thought.